Justin's here. We've got a nice turnout.
Nice. Minimize David.
Michelle.
Michael's in the.
Sure, you'll figure it out. I'm always hearing about how.
Ready whenever you are.
Thank you so much for coming out today, for bearing with our technical problems, for solving our technical problems. Business can really do anything. This is, I think, one of the happiest, most exciting days in the life of a department. You know, it is the culmination, obviously, of an enormous amount of work. It is, I think, very exciting to see what's been going on. It is a very important step in the life of a young scientist and scholar. And it's a very proud moment for me. So I just wanted to give you a little background about some things that Evan has accomplished before he wows you with his research. Just as a reminder of what the structure of this will be, Evan will give essentially a colloquium-length talk for those civilians out there. That's going to be in the range of 45 minutes or so, 45, 50 minutes, plus questions. Clarification questions are welcome, encouraged, frowned upon.
Somewhere in the middle.
Somewhere in the middle, frowned upon. So by all means, and then of course there'll be questions afterwards from non-members of the committee. Okay, so Evan joined the department in 2018 after getting his undergraduate degree at Stony Brook a year earlier. We started working together pretty much immediately. He had come across a paper that, oh, he's no longer in the screen, but our colleague David Bacon and I had written about a decade or so ago, and was very interested in trying to see, and I'm not going to give away too many details, whether any of this, now that the observing had sort of caught up to the theory, whether any of this could actually be done. And so a lot of what we did early on is we did a lot of really interesting stuff in gravitational lensing. Evan is on 3 papers since he's been here, and preparation for a 4th. So one is third author, one is first author, and one, maybe he'll tell us about it, as solo author. He incidentally was a 4-time winner, 4 times of like best TA, basically. And what's more is, I mean, I sort of indicated this in my comments about like just basically sort of seeking out and saying, this is what we want to do almost immediately. He has been the driving force in just about everything we've done. He, you know, took the lead in sort of becoming partner, external collaborators with the Dark Energy Survey and members of the weak lensing working group. He's presented at the Dark Energy Survey collaboration meetings at AAS. He's had invited talks at Sussex or Essex? I was confused. Sussex, and Portsmouth. He wrote most of the science for our funded NSF proposal that funds this work and will fund some of its successor work. And I'm pleased to say that his contributions will not end once we successfully grant him the PhD, which I'm convinced we will. But he has a long-term appointment at Bryn Mawr starting, I think, tomorrow, basically. This is, you know, despite the fact that I've been involved in this is still very exciting work to hear about. There's things we've discovered in the last few months that are really, you are the first people to officially hear about. And I'm just so pleased and so impressed with everything that you've done. I'm looking forward to hearing, tell all these good people about it. Thanks.
Thank you. Thank you all for coming. I'd like to start with a picture to orient ourselves. This is a picture of the night sky. And in parts of the world with a typical amount of light pollution, this is what you see, a bunch of stars, maybe see some planets. Usually mostly what you see is a bunch of dark, empty parts of the sky. In 1995, the Hubble Space Telescope was pointed at a particularly dark and particularly empty-looking region of the sky, outlined there in yellow. It's about 1/13 the size of the moon on the sky. With an exposure time of about 10 days, the image that the Hubble Space Telescope took is one of the most astonishing in astronomy. It's known as the Hubble Deep Field. Almost all of the objects in this image are galaxies like our own. So the Hubble Deep Field is a snapshot of what we might call the late time universe. And by observing these galaxies, how many there are, their shapes, how they cluster together, we can learn about cosmology. As we will discuss, current cosmology surveys take pictures like this across huge parts of the sky. A good model of cosmology needs to be able to explain how we go from tiny fluctuations immediately following the Big Bang that are imprinted on the cosmic microwave background that we can observe, all the way through structure formation to give that picture of the Hubble Deep Field, of those galaxies that trace the large-scale structure in the universe. The best cosmological model we currently have that is consistent with our numerous and varied cosmological observations of both the early and the late universe is the lambda CDM model. And that says that the universe can be described in terms of an accelerated expansion by the cosmological constant, which we understand as dark energy, structure formation by cold dark matter, and is governed by the law of gravitation described by Einstein's theory of general relativity. You've probably heard of this pie chart on the left of the energy budget of the universe. I just want to point out that this little sliver here, which we cosmologists call baryonic matter, and in reality is everything in this room and everything on Earth and everything that we can see, makes up about 5% and doesn't even get a letter in the acronym lambda CDM because cosmologists have deemed it very unimportant. But it turns out that for what I am going to be doing, it's very important, and we will come back to that later. So let's discuss the idea of the large-scale structure of the universe. So by large scales, we mean on the order of 100 million parsecs, parsec being about 3.26 light years. And by large-scale structure, we're referring to the large-scale distribution of matter across wide regions of the observable universe. So we compress measurements of large-scale structure into statistics. And it's useful to define the matter over density, which is the excess density at a given location relative to the mean background density. And this matter over density is time dependent, right? Tiny fluctuations grow into large-scale structure over time. As we will discuss, the formation of structure depends not only on time, but also on scale. At the largest scales, the matter over density is small. And as we zoom into smaller and smaller scales, this matter over density becomes quite large. And so to describe a time-dependent, scale-dependent picture of structure formation, it's useful to Fourier transform this matter over density in 3 dimensions and decompose it into Fourier modes. Now, we are simply not interested in, and in any case, we can't know the exact value of the matter over density everywhere in the universe, but we can describe the statistical properties of this matter field. So the variance of these matter over density Fourier modes, which is the 2-point clustering statistics of the over density, define the key statistic of structure formation, the matter power spectrum. This particular plot is the linear matter power spectrum, which assumes that the evolution of the matter over density is well described by linear theory. We see that the amplitude of the power spectrum increases from the early universe, or high redshift Z, to the late universe, or low redshift Z. And that indicates a growth of structure as the universe evolves. The shape of the power spectrum changes as a function of scale or co-moving wave number K. So to the left of the peak are very large scales, which we understand very well in the context of inflationary cosmology. And to the right are smaller scales. The peak of the power spectrum is related to a time in cosmic history where the universe goes from being radiation dominated, where structure growth was suppressed, to matter domination, where structure grows. So that's why there's this turnover in the power spectrum. I just want to point out that there are these wiggles to the right of the peak, and these are known as baryon acoustic oscillations. And these are the results of the behavior of the photon baryon fluid in the very early universe. And it's imprinted on the linear matter power spectrum in a very predictable way. So the linear power spectrum is a very precise description of the universe down to some characteristic scale, K nonlinear. And beyond K nonlinear, our linear approximations break down. Structure at these scales collapse and then hierarchically assemble into larger structures as the universe evolves. Right, so this nonlinear structure can be well described by halos, which are bound cold dark matter structures. And one of the main methods for describing nonlinear structure and computing the nonlinear matter power spectrum is that of n-body simulations plus the halo model. So as you can see, K nonlinear sort of encroaches on larger scales of the universe, evolves from early to late as nonlinear structure grows. And this is because at earlier times, structure was not as evolved. Right? So the nonlinear scale was smaller. Now, an assumption of the nonlinear matter power spectrum is that baryons simply behave as cold dark matter and follow their evolution. And this assumption breaks down as we approach very small scales. So the baryonic effects at these scales are different from the baryon acoustic oscillations imprinted on the linear power spectrum, which we can predict. And as we will discuss later, the baryonic physics at these scales affects the matter power spectrum in a non-negligible way, such that n-body simulations and the halo model cannot accurately model the distribution of matter. Right? And so the precise way in which it modifies the nonlinear matter power spectrum is not well constrained. It's very much an unsolved problem. And my work represents an attempt at offering some tools to study that. Before we get to that, let's talk about one of the ways we can use observations to study any of this large-scale structure. And one of the tools we have to study cosmology is gravitational lensing. So a prediction of general relativity is that massive bodies deflect light that passes by them. And the consequence of this deflection of light is that massive bodies behave as a lens, the analogy being light refracting through some glass lens. So I want to talk about the simple gravitational lens system. So first you have some source of light, which is typically some galaxy in the background. And then you have a gravitational lens, which in this case here is some massive cluster of galaxies. And then you have an observer, which is us in this case. So as light leaves this background galaxy, it is deflected around the cluster, and we observe gravitational lensing. As it turns out, the more massive the lens, the more deflected the path of the light is. So by measuring gravitational lensing, we are able to figure out how massive the lens is. So an example of a gravitational lens you may be familiar with is this galaxy cluster, SMACS 0723. Probably you don't know it by name, but maybe you saw it in the news in 2022. This was one of the first publicly released images from the James Webb Space Telescope. So when you have an extended object like a galaxy that is gravitationally lensed, it looks different than it would if there was no lensing. Shape changes. So we can see that a little bit in this image. So for context, I want to delineate some of the things that we're looking at here. You probably noticed this spiky thing first. That's a star within our own galaxy. Just ignore that. that's just getting in the way. I want you to look here at this white globish part of the image. This is the galaxy cluster in the image, right? So there's a visible part of it. Most of it is dark matter that we can't see. So there's actually two different types of gravitational lensing in this image. And what's being lensed are all of these galaxies in the background, these red and these blue galaxies. They are not part of the galaxy cluster. They're really far behind it. So the first type of gravitational lensing you can see in this image is strong lensing. And this is what happens if you have a background galaxy that's directly behind the lens. It gets extremely distorted. If you notice these arcs around the cluster, these two arrows are pointing to what is actually two images of one single galaxy. There's another type of lensing, which is the type of lensing that I study, which is weak lensing. And this is what happens to the background galaxies that are further away from the center of the image. Their shape is slightly distorted. So we can quantify gravitational lensing by something called the lens equation. So when a gravitational lens deflects the path of light, it changes the apparent position of a source galaxy on the sky to the lens plane coordinate theta from the source plane coordinate beta. And these coordinates are related to each other by derivatives of the lensing potential, which encodes information about the distribution of matter along the line of sight. And this formalism can be used in order to define the weak lensing fields. And the idea is the following. If you imagine taking the lens equation out to second order, the first order terms, which corresponds to the various second derivatives of the lensing potential, get you the weak lensing shear and convergence fields, gamma and kappa. Right, so we can take a look at what these actually look like with this image on the right. You imagine starting out with some perfectly circular background galaxy, and we can think about what different weak lensing effects can happen to it. So convergence is this isotropic spin zero effect. It just changes the apparent size of the image of the galaxy, whereas shear is an anisotropic stretching effect. So if it takes a circular looking galaxy and it stretches it into an ellipse. Seen here and here. I just want to point out that 1 and 2 in this formalism refer to the X and Y coordinates on the sky. This is where most astrophysicists and cosmologists stop. The vast majority of weak lensing research just makes use of shear. There are, however, more lensing fields beyond shear and convergence. The second order terms, which correspond to the various third derivatives, get you the weak gravitational flexion fields, F and G. And these fields are interesting for a few reasons. First of all, you can observe both F and G, whereas with shear and convergence, you can really only observe shear. You also notice that the F flexion is the derivative of the convergence, the G flexion is the derivative of the shear. Over on the right, you can see what F and G look like. F is a centroid shifting effect. It's spin 1, can pretend that it's a vector. G is a much more complicated spin 3 triangular distortion. When you observe a weakly lensed galaxy, you end up observing a combination of all of these fields. So starting with an unlensed galaxy, adding shear, adding F flexion, and adding G flexion, you end up with a banana. So this is why flexion is often referred to as the banana-ness of a galaxy. So as I said, in the vast majority of weak lensing research, people use shear. I'm going to talk more about the dark energy survey later, which is a large collaboration I'm involved in. There's at least 100 people working on shear in the dark energy survey, and it's very much a collaboration-wide effort. The people working on flexion in the dark energy survey are myself, Dr. Goldberg, and Dr. Bacon, and that's almost the end of the list. So there's a pretty big disconnect in how often these different weak lensing signals are used. So it's worth talking about why it is that people use shear, where it's useful, and why we might actually want to be looking at flexion. So here's a simulated example of a common application of shear, and using it to measure the mass of a galaxy cluster. So the galaxy ellipses, which are represented by these lines, tangentially align themselves around a galaxy cluster. And averaging that signal lets you recover the underlying shear field. And this is an excellent way to measure the total mass of the galaxy cluster. Flexion, on the other hand, is more sensitive to small scale substructure, since it probes the gradient of the density field. And here you can see how the F flexion is responding to these smaller mass peaks that the shear does not respond to. Okay, so how do we actually measure weak lensing? How do you measure the shear and flexion of an individual galaxy? So the process of weak lensing measurement is non-trivial. The journey begins with the intrinsic properties of a galaxy. Galaxies have some intrinsic ellipticity, and they even have some intrinsic flexion. Galaxies inherently can be an ellipse, and they can inherently be a banana. If that galaxy is lensed, the shear makes the galaxy look more elliptical, the flexion makes it look more like a banana. But this alone is not what our observation of a galaxy looks like when we look at it through a telescope. As the light from the galaxy passes through the optics of the telescope, the image is smeared. And then worse still, if it's a ground-based telescope, that light has to go through Earth's atmosphere, where it smears the image even more. We quantify this by something called a point spread function, how much it spreads out one point of light. Then after the light passes through the telescope's optics, it's collected by the instrument's charge coupling device, or CCD, where it's pixelated and stored. And then finally, there's also noise in the image from the sky and from the CCD. So this noisy and pixelated and smeared image kind of represents the worst case scenario. Not all of our observations look quite so pathetic. I should note that if a galaxy is lensed, you can only ever measure the combination of the galaxy's intrinsic shape plus its lensed shape. So that means to recover a weak lensing signal, you need more than one galaxy. And by measuring the observed ellipticity, for example, over many galaxies and averaging over that, you recover the underlying shear field. And same is true for flexion. So early in my PhD, I wrote a code called Lenser, which is a Python code which can measure the flexion and ellipticity and other shape parameters of a galaxy. The code itself can be found on GitHub, and the details of the pipeline can be found in a paper published in Monthly Notices by Drexel alum Dr. Joseph Fabricius, myself, and Dr. Goldberg. I'm going to take you through some of the relevant details of the pipeline here. So Lenser takes as an input an image of a galaxy, along with a source extractor segmentation map, a weight map, and some model of the point spread function for that instrument. And so Lenser assumes that the galaxy is well described by a Sursig model for its brightness profile. All right, and so some of the parameters of that model are the ellipticity and the flexion. And so because of the large size of this parameter space, Lenser gets a first guess on the parameter space through image moments in the image, and then there's a local minimization of this chi-squared fit of the model to the image. Out comes the best fit parameters, and that is what constitutes a measurement of flexion and ellipticity. So I've recently made some big updates to the software, and it's now capable of multi-band, multi-epoch fitting. So I want to talk about what that means. So Lenser pipeline that we just discussed would be Lenser operating in what we would call single fit mode, where the input galaxy is just a single image of a galaxy. So this is going to be, by definition, a galaxy imaged in a particular photometric band or filter. So maybe it's an R band image of a galaxy in the language of SDSS filters. But regardless, it's a single postage sample of a galaxy, but it's very often the case that you have a galaxy imaged in multiple bands and in multiple epochs, an epoch being just an exposure, could be within one band or across multiple bands. So the Lenser multi-band, multi-epoch fitting fits a single model to all available bands and epochs. And we found that this improves the overall flexion estimate and also successfully gives fits for more galaxies from a given subsample. Get a higher success rate. So Lenser is the only multi-epoch flexion code, and it's the first open source Python flexion measurements pipeline. So now that we know that we can measure the flexion and the ellipticity of individual galaxies, how do we turn these weak lensing measurements into constraints on cosmology? The image you see in the background here is an observation of the southern sky by the Dark Energy Survey, or DES, or DES, depending on if you're American or from the UK. DES is one of the main cosmology surveys in operation today. It's collected 6 years of observations on the 4-meter Blanco telescope in Chile using the dark energy camera. And this wide field survey has observed 5,000 square degrees of the sky in multiple filters. In DES Y3, which constitutes the first 3 years of DES data and is the most recent data release at the time of this work, there are roughly 100 million galaxies that can be used for weak lensing analysis. This is the largest weak lensing data set on the market. And so what is it that DES actually does with the images of 100 million galaxies across 5,000 square degrees of the sky? One of the main key projects of DES is to look at how weak lensing and galaxy clustering can constrain cosmology. The current state-of-the-art observable in wide field cosmology surveys these days is something called the 3x2 point function, which is illustrated in this cartoon made by Dr. Jesse Muir from the Dark Energy Survey. In the upper panel are these small yellow circles. These represent the background or source galaxies. Light leaves these galaxies and is continuously perturbed by large-scale structure before reaching the Dark Energy Survey telescope. The orange circles are these foreground or lens galaxies that trace the large-scale structure by clustering. And in the bottom panels, you'll see these elongated yellow ellipses. Those are the sheared images of the background galaxies. And again, they are lensed by that intervening large-scale structure. So the 3x2 point function is a collection of 3 different 2-point correlation functions. The first is cosmic shear, which is an 2-point ellipticity correlation function. So 2-point cosmic shear is a measurement of the excess probability of the apparent ellipticity of 2 galaxies being correlated as a function of the distance between the pair. Galaxy clustering is a 2-point function describing the excess probability of the positions of foreground lens galaxies being correlated. And then galaxy-galaxy shear is the cross correlation between the position of foreground lens galaxies and the shape of background source galaxies. So I'm going to go into more detail about one of these correlations, which is cosmic shear. So this is a simulation of large-scale structure with some blue ellipses added in, and the blue ellipses are lensed by this large-scale structure, and then we have a visualization of what the cosmic shear looks like. It's this tangential alignment of the galaxy ellipticities around the large-scale structure. And this plot shows where cosmic shear probes the matter power spectrum. So these are the DES year 1 measurements here in yellow. And cosmic shear probes modestly large to modestly nonlinear scales of the power spectrum. So DES uses the 3x2 point function to constrain cosmological parameters and understand cosmic acceleration. And cosmic acceleration is an important goal of the dark energy survey because there is some tension in measurements of cosmological parameters between low redshift or late universe surveys like the dark energy survey versus high redshift or early universe surveys that probe the cosmic microwave background. Within the DES Y3 data, the dark energy survey has achieved excellent constraints on cosmological parameters such as omega m, which is the matter density parameter of the universe, sigma 8, which is related to the amplitude of the matter power spectrum, and the dark energy equation of state parameter W. And so this is great. So what's the problem? This is the full-blown DES year 3 data vector of the galaxy clustering, the galaxy-galaxy lensing, and the cosmic shear. So in these plots, what seems like nearly half the data is grayed out. So what do you suppose those gray regions of these plots mean? It turns out that these gray regions represent parts of the data vector that are thrown out. So everything in gray is data that is not used to constrain cosmology. This is a huge amount of data with a lot of constraining power. So why is all this thrown away? Well, it's because it's measurements at small scales. So to turn measurements of the 3x2 point vector into constraints on cosmological parameters, you need to be confident in your underlying model, which is, in this case, the lambda CDM model of the universe. The problem is that the small scale power spectrum and the baryonic effects on it are poorly understood. And the plot on the left illustrates the huge variation in predictions of different models of baryonic effects. And they differ from each other by tens of percent. There exists something known as baryonic feedback, where active galactic nuclei and supernova heat up the local environment, which suppresses the growth of structure. There are also processes that can cool gas and in turn increase the growth of structure at even smaller scales. And it gets very complicated when deciding how much weight to give to each of these effects in your models and in these simulations. And you end up with a very wide variety. If you want to take the data and constrain large scale quantities like omega m and sigma 8, you don't want to use a data vector with extremely small error bars to constrain a model with extremely large variation. So there's therefore a need to understand the small scale matter power spectrum. And if we had good constraints on it, we could better understand how to model it. And if we understand how to model it, we can use some of those scales to constrain cosmological parameters. So this is where my work comes in. So what if we were to take the general principle of cosmic shear and extend it to flexion? And so that would be cosmic flexion, the flexion correlation function originating from the large scale structure of the universe. On the left is a cartoon of what the cosmic F flexion would look like with these vectors aligned with the large scale structure. So while cosmic shear has this broad peak over various scales, cosmic flexion peaks at much smaller scales than does cosmic shear, making it more sensitive to the small scale power spectrum. So cosmic flexion could offer constraining power at small scales, where the shape of the power spectrum is poorly understood. So the original idea for this was proposed by, I call them the big two of flexion, Dr. Goldberg and Dr. Bacon, both of whom are here and my advisors, and Rowan Taylor in this paper in 2005. But there did not exist any cosmological surveys at the time that would allow something like cosmic flexion to be measured. It's a much weaker and harder to detect signal than cosmic shear. And then the full theoretical formalism was laid out in this paper, Arena et al. In 2022, and was the subject of a significant portion of my thesis. And a lot of theory work went into a full description of cosmic flexion. including signals not considered in the original paper, as well as the discovery of completely new signals. I will review some of the results of that work here. So cosmic shear and flexion are measured on pairs of galaxies, a galaxy pair I, comma J, in real space. If you remember those 2-point correlation functions we were talking about earlier, we could write a generalized 2-point correlation function in the following way. And what this means is if some lensing field A, could be shear, flexion, at the position of galaxy I correlated with some lensing field B at the position of galaxy J, and they are distance theta away from each other. So the well-known cosmic shear 2-point correlation function is the correlation of the shear of galaxy I with the shear of galaxy J, binned by angular separation theta and averaged over all pair combinations. So my work extends this, generalizes this idea, adding flexion into the mix, which adds a lot of information. So first of all, you can measure the F flexion of galaxy I and correlate it with the F flexion of galaxy J. But if you remember, there's 2 flexion fields. So you can also do that with G. And so with cosmic flexion, there's already twice the amount of signals that you can measure as compared to cosmic shear. But there's also cross correlations. So the F flexion of galaxy I is going to be correlated with the G flexion of galaxy J. Then things really start to get interesting when we found that there actually exists a cross correlation between the shear and flexion of galaxy pairs. And this is a cosmic shear flexion 2-point correlation function. The idea is that every galaxy is shear and F and G. So you start building a very large number of correlators for a single galaxy pair. And then finally, one point that you can correlate the shear of galaxy I with the flexion of galaxy J, and also the flexion of galaxy I with the shear of galaxy J. You get twice the amount of information from cross correlations as compared to autocorrelations. So in case you were curious or you were concerned that you're not seeing a lot of math for the theoretical physics talk, calculating those theoretical cosmic flexion functions involves some pretty nasty math. And here some of it is. If you want to see it, you can find it in the Arena et al. Paper. But I do want to point out that these are the theoretical 2-point functions, and they are blah, 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 somehow related to the matter power spectrum and come out of predictions of that. So I want to talk about what those theoretical predictions are, given a cosmological model. So these are 2-point correlation function theory predictions for a dark energy survey year 3 property with a Planck 2018 cosmology and a nonlinear matter power spectrum that is extended to small scales in a way that's described in that Arena et al. Paper. On the left are the various flexion correlators, and on the right are the shear flexion correlators. So this is arc seconds on the x-axis for the flexion. And so the cosmic flexion signals peak at points where galaxy pairs have very, very small separation on the sky, about an arc second. The shear flexion also peaks at those scales, but has a bit of a more broad peak, and it sort of approaches the arc minutes territory and bridges the gap between the flexion and cosmic shear. So with the inclusion of cosmic flexion, along with cosmic shear, we can measure large scales, nonlinear scales, and small scales. You might notice also, by the way, some wiggles on these functions, and these, you could think of these sort of as errors from the numerical calculation of these functions. So going from the power spectrum to these functions involves a very poorly behaved integrand, the details of which are also described in that paper. So for the finale of my PhD, I've measured the flexion of every galaxy in the DES year 3 field. And the starting point here are the DES year 3 photometric data set stored in what are called multi-epoch data structures or MEDS files. and I use information from the R, I, and Z bands. So this 5,000 square degrees of DES year 3 data is broken up into 10,000 tiles. We get a meds file for each band, for each tile. And within each of those tiles, you get about 10,000 objects, not all of which are galaxies that can be used for weak lensing. So I feed each object in Y3 into my lenser pipeline in the RIZ multi-band mode. And this is very much a big data problem. The CPU hours required to run every object in Y3 through lenser is 1 million CPU hours, which means if you were to start running that on your laptop, it would take 114 years. As much as I'd like to think I'll still be around by then, I will not. But this is what supercomputers are for. Instead of running this in series on one computer, it's run in parallel over n computers, and you reduce the runtime by 1 over n. So these calculations were run on the Sharma supercomputer at the Institute of Cosmology and Gravitation at the University of Portsmouth in the UK. It's got a very impressive name. Using a modest amount of computing resources, this calculation took about 4 months. So to parallelize lenser, I made use of a code written by the man who taught me every single thing I know about supercomputers, Dr. Sean Lewis, who's nice enough to come today. And that code is Python OpenMPI. The end result of all of this, after selection cuts, is 45 million galaxies with measured flexion and ellipticity values. And this constitutes the DES year 3 weak lensing flexion catalog. And this is the largest flexion catalog ever created. So here are some sky maps of the F flexion components in the DES year 3 flexion catalog. And the blue outline is the DES year 3 footprint, which looks like a tank, oddly enough. And again, this is flexion measurements on 5,000 square degrees of the sky, which is a quarter of the southern hemisphere. So let's talk about using this flexion catalog to measure cosmic flexion for the first time. So we talked about what a 2-point correlation function is, and that we measure it in real space on galaxy pairs. But let's talk about that a little more. So because of the fact that, again, when you measure a lensed galaxy, you're measuring the intrinsic shape plus the lensed shape. Calculating the 2-point correlation functions on pairs of galaxies, it is a noisy estimator of the underlying true lensing 2-point correlation function. And that estimator is written here. I have a pseudocode snippet here on how you calculate this. And what's going on here is pretty straightforward. It's just calculating the mean in a for loop. Right, so for I in n galaxies in your catalog, for j in n, you just store the mean, you calculate it iteratively, and you're good to go. But there's an assumption here that we typically don't really think about. We're saying that the maximum likelihood estimator is the mean. Here's a plot of one of the DES cosmic shear 2-point functions. There's a lot of them because they split them up into tomographic bins. The data points are measurements of the 2-point correlation functions in angular separation bins. So the estimator implies that the data point is the mean of a Gaussian distribution, the error bar, the standard deviation over the square root of the number of pairs. And this is indeed exactly what's going on inside of, for example, this bin here in the cosmic shear field. But we found something interesting with cosmic flexion, which is that the underlying distributions of the signal are non-Gaussian. They're heavy-tailed distributions. Outliers in these tails affect the estimate of the mean so much that the mean is not the maximum likelihood estimator of this distribution. And we find that median statistics are more appropriate. But this represents a serious computational challenge. The mean of a 2-point function is easy to calculate. You can calculate it iteratively inside of a for loop. But you can't do that with the median. You need to store to disk or hold in RAM the entire set of pairwise calculations and then calculate the median on that. And the number of pairs is of order n squared, where n is 10 to the 7 in this case. So we're talking about terabytes of disk storage. This is indeed doable on the Sharma supercomputer, but we're really pushing it. So I wrote a code that can handle all these calculations, both the mean and the median statistics for all the 2-point correlators. It's called F#, and it can be found on GitHub. The input is the DES year 3 flexion catalog. The output comes the DES year 3 cosmic flexion measurements. So I'd like to show you for the first ever measurement of cosmic flexion. So here you see the shear flexion data vector. Again, this is using median statistics, error on the median. These are the data vector of the 8 shear flexion correlations. The green line is the theory predictions from the fiducial cosmology that we mentioned earlier. These measurements don't look terribly interesting by themselves, but in fact, we can draw conclusions from their combined statistical significance. They all are probing the same power spectrum. So if we assume a likelihood of this form and we adopt a 1-parameter model where we simply apply a normalization factor to the fiducial cosmology theory vector, this fancy n here, where if you get a measurement corresponding with n equals 1, that means that it agrees with theory. You can then maximize that likelihood to get a measurement of n and the error on n using some jackknife resampling. And here are the constraints that I get. So whether you're using the whole shear flexion data vector or just the higher signal to noise shear F part of it, you end up with a roughly 3 sigma rejection of the null hypothesis while being consistent with theory predictions to within 1 sigma. And this constitutes the first ever detection of a cosmic flexion signal. If you want to see something not as great, here's the flexion results. So we have every reason to believe that 2 of these signals, FF plus and GG plus, are completely contaminated by systematic effects. We believe that we do not have perfect subtraction of the point spread function, which affects these signals and these signals only in this extreme way. And then if we make use of a data vector without those 2 signals, we still get a result that is inconsistent with theoretical predictions with this value of n, not agreeing with 1. So there are still systematic effects present here. So for the initial release of these results, we will only claim the shear flexion signals as detected. So while there is certainly information within the flexion signals, it's a question of whether we can remove the small scale systematics. The fact that these systematics vanish for the shear flexion signals, but not for the flexion give us some insight on how to move forward, indicates that there may be some residual flexion gradient at small scale, some flexion blending at small scales, perhaps some intrinsic alignments. I should note that there are also a number of large-scale systematics in the flexion catalog as a function of survey property, but we are confident in our ability to remove those. And I should also mention that we see no evidence of any B-mode systematics in this data. But owing to the complexity of these small-scale systematics, resolving the flexion data vector will be left to future work. So to close, I want to discuss the future of cosmology surveys. So we're currently transitioning from stage 3 experiments, such as the dark energy survey, to stage 4 experiments, such as the Rubin Observatory Legacy Survey of Space and Time, LSST, Euclid, the Nancy Grace Roman Telescope. LSST and Euclid in particular are going to observe both wider and deeper fields than the dark energy survey does. About 20,000 square degrees, I believe. So this increase in the galaxy sample for the weak lensing is going to give even tighter constraints on cosmological parameters. And while this is very exciting, it also represents a serious challenge that we will have to deal with. As the measurements get better and better, the 3x2 point analysis will have to throw away even more scales due to the uncertainty in the cosmological model and the shrinking of the error bars. That is unless we can also improve the theory predictions well enough to meet that challenge of improved measurement. So if we can understand these small scale power spectrum and can model cosmology better and better to smaller and smaller scales, we can use more and more of that information that will be available in these stage 4 surveys. So cosmic flexion could potentially play a role here in these stage 4 surveys because you have more galaxies per unit area and you end up with more galaxy pairs at the small scales, the cosmic flexion probes, which gives a huge boost in the overall signal to noise of the cosmic flexion signals. The hope is that we can use the information we already have, measurements of the 3x2 point function, combined with some of these novel probes of small scales like cosmic flexion, to place constraints on these small scale power spectrum, which will in turn inform theory and allow us to extract the maximum amount of cosmological information from future surveys. In terms of the physics at small scales, I mentioned the baryonic physics at small scales that could be constrained. In a paper I wrote in 2022, I examined how there also exists the possibility of a landscape of modified gravity theories that recover general relativity at large scales, but deviate from it at small scales, again, owing to the lack of constraints that we have at small scales. And so I investigated what cosmic flexion would look like in this paradigm. Then other people have suggested that cosmic flexion could probe other interesting physics, such as primordial non-Gaussianity and vector and tensor modes from the early universe. So cosmic flexion has the potential to be a very exciting part of the upcoming era of cosmology. So first, I want to acknowledge all of these institutions. I started my journey in physics at Brookhaven 12 years ago. I was lucky enough to be a summer intern. I was fortunate enough to go to Stony Brook, then Brookhaven again, and then I'll be here at Drexel. And then my next stop will be Bryn Mawr, and this cosmic flexion work will go on. I want to thank my friends and family who have all sacrificed in some way for me to be here. Thank you to my parents, to my brother Mike. Thank you to Lauren. You got me through the most difficult parts of this PhD in the job search and put up with all of it. I want to thank my committee, Dr. Dolinsky, Dr. Richards, Dr. McMillan. Thank you to my co-advisor, Dr. Bacon, who went above and beyond. And thank you to Dr. Goldberg, who is the best advisor I could have asked for. I want to thank my fellow graduate students, Jacob, Dr. Sean Lewis, Dr. Andrews, many, many people on this list and off this list. And I also want to acknowledge again, I would not have been able to complete this computational work without Sean and Anthony, one of my Stony Brook comrades. They taught me everything about computers. And thank you to the physics department, to Lisa, to Evan. And I want to thank Dr. Rachel Krautzer, who's currently teaching. I would not have made it to Bryn Mawr without her mentorship. So there were many points in my life where I never thought I'd be lucky enough to defend a PhD, but I always dreamed about it. So thank you all for coming. And I'm happy with the help of Dr. Goldberg to take any questions.
To be clear, I have no intention of answering the question. Any questions from the room? And also I'll put in a query in to see if anybody online has any questions. Yes.
Well done, first of all, Evan. So I have two questions. One, to get information about the distribution of matter from lensing, you have to know something about what stuff looks like before it's lensed. But how can you do that if you can't look at anything that hasn't been lensed? Understand?
So are you talking about how do you recover the amount of weak lensing that there was?
Well, you said at one point that galaxies have some intrinsic lensing,
Right.
right? So how do you decouple that from the flexion that occurred due to lensing?
That's a great question. So what you can do is you can look at a field of galaxies where you assume that there's not really any lensing. There's always some amount of lensing, but you can correlate on patches of the sky, it's like parallel fields next to galaxy clusters, where you assume there's no lensing. And you can correlate them in a certain way where you're essentially probing at the highest signal to noise, the intrinsic properties. in that
Find
respect.
a good spot to look at.
You gotta find a good spot to look at, yeah, that's exactly right.
But my other question is, I think it was slide 34 or something, one of the later ones. You have the shear flexion data set, which agreed with theory more or less, and your flexion data set, which doesn't. And you say that the one that doesn't agree with theory must have something wrong with it. I mean, is this a little like confirmation bias?
Yeah, that's a very good question. The question being, why do we believe one set of these signals as opposed to the other one, given the fact they come from the same data? The shear flexion and the flexion signals behave very differently. One thing that's very different is with the flexion, for example, with these two signals, you're correlating F and F. So any systematics that are there are really exaggerated and correlated together, and they carry over into this. And it's likely also the case that that happens even with F and G, because again, they're similar. And also the spin properties of them, when you combine flexion and flexion, you get this even spin combination, and things don't always rotate away. Whereas the shear flexion, you are subject to a different type of systematics, where you're dealing with the systematics from the shear correlating with the systematics from flexion. A lot of that tends to go away.
Sure.
I appreciate it.
Other questions? Oh, we have one. Oh. Well, David says he has 3 questions to ask, but David, you can wait until we're grilling him. Unless there's clarifications, but we're gonna grill him once we kick everyone else out. Hopefully you heard it.
While we're on this page, what would you say are some of the leading contenders for the systematics that you want to look at?
Mhm.
That is throwing this off?
So the by far the worst signals here are FF plus and GG plus, these two. And we are really confident that the dominant thing that's causing that is misestimation of the point spread function. Because that carries over into the plus combinations of signals with the same spin. So that's why you see that with FF plus and the GG plus. Whereas when you look at the other signals, that PSF effect doesn't carry over. It has to do with the fact, actually, that these two signals are the same in the rotated versus the unrotated frame. So they pick up any correlation of systematics that exist in the unrotated frame, and they carry over. And so other effects here, we suspect that there's some level of flexion selected blending. And it's a little hard to draw conclusions from each of these signals individually. It's a little hard whether or not to trust G owing to its complicated spin property. We're not sure how well we can subtract the G systematic effects at this level. And you're really just left with sort of one signal that is a contender. It's hard to draw some conclusions from that, but we think things like blending, PSF, different properties of the survey footprint, like air mass, throwing that off as well.
We have a question incoming from Professor Bowley.
Okay.
I'm typing. Actually, you might be able to see it too.
Dave, do you want me to type or do you want me to talk?
Oh, well, you.
I can, yeah, we can hear you if you would like to talk as well.
Sure.
Sure, it's probably quicker for me to talk real quick. So dangerous to ask the theorist to opine about observations, but sometimes quite helpful, given that a strong limitation on what you can do is point spread function issues.
Mhm.
Are there recommendations for observing strategy? There are things one can do in taking the data that would allow one to ameliorate point spread function effects. I mean, you can image a galaxy in different parts of the focal plane. You can take it at different times. I mean, the problem with space-based instruments is that you have PSF variations not only across the focal plane, but in time as there are thermal variations. So just curious whether you might have thoughts about this, or maybe that's a project for the future before people take all of these data for stage 4 experiments. Are there things they could do that would make those data more helpful for this type of measurement?
Yeah, that's a great question, and there definitely are. So the point spread function modeling is extraordinarily sophisticated for the cosmic shear and the galaxy lensing stuff in the dark energy survey, which it has to be because it's a big PSF, right? It's a ground-based telescope. And so there's a battery of systematics that they do with that, but they don't model flexion because they don't use it. So a step would be to have some robust modeling of the flexion properties of the PSF. That absolutely needs to happen. And yeah, that represents a significant amount of work, probably a PhD's worth of work to get it at a level for stage 4. That's my answer to that. But my preferred answer is I'd rather just use Euclid in the future, the smaller PSF, because we've found that flexion can be pretty insensitive to smaller point spread functions. So Euclid might help a lot in that regard as well. But yeah, there needs to be a lot of work done to that.
Other questions from the room or from online?
I don't have a question, I just have a statement, is that okay? So proud.
Thank you.
Well,
Thank you.
I have no idea what you're.
It's great to see you.
And you owned what you were saying.
Thank you.
We're proud.
Thank you. Thank you.
Love you. And if anybody, you feel him, come
Oh. Well, with that, thanks for everyone, for coming. You may wait in the hall, or you may wait at a coffee shop or something to stay a little while. The committee, should stay. I think there's still some refreshments in the back.
There are.
Ideally, if the committee could move up to the first couple of rows, so we're not quite so spread out. And would you mind putting, David,